Okay, I wanna make a video about this example that I just went over. This is that function 2 to the x where we were doing a linearization at x equals 3. So there's our linearization. And this is going to be sort of an unscripted video. I just decided I wanted to try to explain something about this that takes this example just a little bit further. Down here, we took x equals 3.1 and calculated the error, right? So what I want to show you is how can you figure out the range of values on which the error will be no more than some like maximum amount that you set. Okay, so I just want to show you how to calculate that. So first, let's just draw a little picture. You've got your 2 to the x function, y equals, well, let's call this f of x equals 2 to the x. And then over here is 3. So here's the point at which we do the tangent line. So there's our, there's our linearization L of x, which was 8 plus 8 natural log of 2 times x minus 3. And then the difference between these, so the difference like between these two heights here for some x value, let's call that d. That difference as a function of x is going to be f of x minus L of x. So that's going to be 2 to the x minus the 8 plus 8 natural log of 2 times x minus 3. Okay. So that's the difference. That's d of x. So now, suppose you want to know like what range of values here would be, what range of values around 3 can we have if we want to make sure that d of x, our difference, which is the error. Sorry, I should explain that is what we call the error, the difference in the two functions. What range of values is going to make it so that error is like less than or equal to some maximum error that we're willing to accept? Let's say that we are willing to accept an error up to 1/10. Okay, I just pulled that number out of nowhere. Whatever, it's 1/10. It's some, maybe that's up to one decimal place difference would be acceptable. You can set that error as small as you want if you want it to be more accurate. So the way to figure out what that range would be is just to solve this inequality. Okay, so let's write 2 to the x minus 8 natural log of 2 times x minus 3. And I distributed that subtraction there, by the way, to the two terms. That's our d of x, our difference. When would that be less than or equal to 0.1? That's the question, right? Well, this is not an inequality that is easy to solve by hand. Probably we could solve that inequality by hand by doing a sign chart for that. What we want to do is subtract the 0.1. Let's subtract that from the 8 here. So we have 2 to the x minus 8.1 minus 8 natural log of x minus 3 less than or equal to 0. This whole thing over here, call that a function. I'm gonna call it g of x. And then the idea here is if you graph g of x, it's probably going to do maybe something like this. I don't know, whatever that looks like. You'd want to figure out where it's less than or equal to 0. And where it's less than or equal to 0 is going to be on some interval where it's beneath the x-axis. So if you can find its zeros, right, if you can set it equal to 0 and figure out where that happens, okay, if you can solve the equation when it equals 0, then you'd be able to figure out the interval on which it's going to be less than 0. And you could do a sign chart. You'd get like positive, negative, and then positive, like that. Now, actually setting that equal to 0 and solving it is not an easy thing to do. In fact, the equation solving strategies you've learned in college algebra are not really going to do it for you. This is the type of thing where you really need to resort to technology. So given that this is not a video I'm making on the computer, I'll leave it to you to go ahead and graph this function. Okay, graph this on Desmos, and then you'll see something like this, and then just click on these points here and determine what those x values are. You're going to have an x value here, you're going to have an x value there, and that will tell you the minimum and maximum x values that would give you a range around 3. It should be, 3 should be in the middle there somewhere. 3 should be somewhere in here. And that'll give you a range of values around 3 where the approximation is accurate to within 1/10.